So welcome back to the respiratory system. We're going to get into this video by looking at our oxygen consumption, or what's known as VO2, taking a look at our metabolism, and then get into what are some of the limits of oxygen consumption within the system, and taking a look at respiratory exchange ratios. But first, I've got a 5-minute rewind for you. So, what I want you to do is to think back over the last two videos that you've watched and look at what is our stimulus to breathe? Why is it? What makes us breathe? And how is oxygen and carbon dioxide transported in the body? So, after you've reviewed this information, you can go ahead and restart the video and be able to move on. If you're not familiar with this, go back and watch that other video that we just had.
All right, we're going to move into our last little bit, which is kind of tying up a lot of the information together and talking about oxygen consumption and fitness levels and kind of re-emphasizing it. So when we take a look at the Fick equation, I would know this Fick equation and what these different things mean. These are different ways to be able to write it. So just keep in mind all those different ways in which we can do that. So when we're talking, we've already kind of addressed this earlier in class, but really we would like to be able to measure it in the bloodstream, but that's not, I mean, when I go back and I look at these equations, really we're looking at the content of oxygen in the arterioles minus the content of the oxygen in the veins, and looking at the difference between those two multiplied by what our actual cardiac output is. The only way to actually do this is to go into the bloodstream and put a catheter into your veins and into your arteries, and that's just not practical on a daily basis, nor are we going to get clients to want to do that. So we can extrapolate it by looking at what the rate of oxygen and carbon dioxide is happening within the lungs, so that we can start to make assumptions by this. This is now called indirect calimetry. Instead of having it being direct, measuring in the bloodstream, it's indirect. So we'll actually be looking and calculating this based off of a respiratory exchange between O2 and CO2. Now the caveat is this has to be done with aerobic exercise, and we have to be at steady state at this time. So at least 60 seconds at that given workload before we start measuring it in order for it to be accurate. We looked at some pictures previously, but this is kind of how we measure it. We put up devices to be able to actually measure the gases when we're breathing, and it goes through a great calibration period. And so some different things that we'll be measuring in order to really understand and calculate off what our VO2 might be is we'll look at the volume of the inspired air, right here, our volume of our inspired air, and this is our volume of our expired air, and then we're multiplying our inspired air by the fraction of O2 that is in the inspired air, and we are subtracting from that the volume of our expired air multiplied by the fraction of O2 in the expired air. So it's really looking at how much are we breathing in and what is our percentage of oxygen, and subtracting out what are we breathing out multiplied by our percentage of oxygen in our expired air. And that's going to give us what our oxygen consumption is. And it tends to be pretty correct, give or take a little bit as far as a margin of error. It's not as accurate as if we were in the bloodstream, but it is the most accurate we can get without being invasive. So we talk about this as being a measure of VO2 max. What is our maximum oxygen consumption? Well, there are some qualifications that we have to meet in order for it to be considered max exercise. So one thing that has to have, or at least two of these things need to have been met. One of them could be a plateau of our VO2. So we are watching our numbers of our oxygen consumption, and we keep increasing in work rate, but even if we increase in our work rate, we're hitting a plateau and we don't see a rise in it. That would let us know that we are at our maximum oxygen consumption and are not seeing that number go up anymore. We can also, one of the criteria would be a plateau of our heart rate. So we're increasing our work rate, but our heart rate does not continue to increase. So we have hit our maximum heart rate at that time period. We're going to go into the respiratory exchange ratio in just a minute, but if our respiratory exchange ratio is greater than 1.1, then we can call it hitting our max exercise or our max oxygen consumption. RPE, many of you guys know what that is from previous classes, but it's the rate of perceived exertion on a scale that is a Likert scale from 6 to 20. We need them operating at least a 17 up to 20 to say that we are hitting our maximum oxygen consumption. And then our lactate levels. If we were actually invasively measuring our lactate levels and they were over 8 millimolars, then that would let us know that we are over our VO2 max. So in order for it to be considered a max test, we have to have at least 2 of these things being met. So we talked about this, and there was questions that came up like, how much can you actually increase your VO2 with exercise? So here's a couple of statistics, kind of gathering it together. I wanted to make sure you guys had this information. VO2 max can be increased by about 15 to 20% with at least 20 weeks of endurance training. So we need to have good, solid, consistent endurance training, and that training is usually 60, anywhere between 20 to 60 minutes per day, 3 to 5 times per week, at an intensity that's great enough to elicit increases in VO2 max, meaning at least a moderate to high intensity exercise, 50 to 85% of your VO2 max. And that's when we can start to see increases in that VO2 from about 15 to 20%. So what limits our VO2 max? Like, what is it that makes it so that we stop increasing in our oxygen consumption? All right, so when somebody has a different max than somebody else, what is it that limited them from having a higher maximum oxygen consumption capability? So these are kind of 4 different categories that things might fall into. And I wanted to just kind of briefly talk about which one of these limits which type of people. So having issues with your respiration, the ability for O2 to diffuse from the alveoli into the lungs, or our ability to actually ventilate, what our rate is or how much we can increase, whether it's how much I can breathe or how much is actually being perfused into, like how much oxygen is getting into my circulatory system, or how well oxygen is binding to our hemoglobin. These kind of issues come into play with people who have pathologies of some sort, some kind of a disease, some kind of a propensity for having low iron, whatever the case might be. These are kind of not your traditional issues people will fall into. However, they can affect what your VO2 max is. Over here, our central circulation, the ability for our heart to actually pump everything around, and to the extent that it actually matches whatever activity we're doing. It could also be your hemoglobin concentration or your arterial blood pressure. Primarily, this is what we see with individuals who are highly trained, and it's usually the cardiac output. Basically, they are utilizing so much oxygen at the muscular level, their heart cannot keep up with that production and distribution of it. So this is what tends to limit the elite athlete, that they are utilizing so much oxygen at the working muscle, they cannot beat that blood around enough. Now, if I were to draw a line and cut it across the bottom right here, these 2 other categories are really what limit the non-elite athletes from being able to have a high VO2 max. So some of it is us actually getting blood flow to the working muscle itself. So over here on the left side on number 3, our peripheral circulation, it can be things like we don't have enough capillaries going to that working muscle, right? Part of what happens with training is that we start to increase in our capillary density going to that working muscle. And if we don't have a high enough blood flow getting to the muscle, we can't bring enough oxygen in, and we can't remove enough of the carbon dioxide efficiently that our legs start to give out, right? We get a buildup of metabolites, we have a lack of oxygen, and it makes it so that we can't keep performing at high levels. So that's what a lot of it has to do with. The other part over here on the right side, the muscle metabolism, is that we don't have enough mitochondria that are built up. Part of what happens with exercise training is that we build up our mitochondria, both in their size and also how many we have. And this is going to fuel our oxidative system, right? Because this is where the oxidative system is all occurring. When we go back to those energy systems, it's all happening in the mitochondria for our oxidative system. It can also be that we don't have enough enzymes to be breaking everything down, and that increases with exercise as well. So somebody who is not elite athlete, they're just either sedentary or just recreationally trained, or even at it could be that they're in good shape, but we're just still limited by the enzymes that are being created to help with all of our breakdown, and also with the number of mitochondria. There's other things listed there under those categories, but those are the main limitations. So here we have disease is usually the issue. Here we have, this is where our elite athletes are, mainly coming from the cardiac output not matching what's happening at the working muscle. In our non-elite athletes, it's usually blood flow. We don't have enough capillary density in order to actually get enough blood flow to the working muscle, or we don't have enough mitochondria or enough enzymes for all of the fuel and metabolism that needs to be happening. So those are kind of what limits our VO2. So when we're looking at the energy use, it's good for us to know kind of what is being oxidized. Is it carbohydrates? Is it fats? In rare occasions, it might be proteins. And this really is going to dictate the amount of O2 being used, with having fat producing the most O2. I mean, that's really a lot of where our oxygen consumption comes from. However, it can also be from our carbohydrates, a little bit from our proteins here. So as we talked about with our indirect calimetry, it measures our CO2 being released, or can, and also our O2 being consumed. We've already focused on what the O2 being consumed is. However, we haven't really talked about measuring the CO2, and why is that actually important? Well, why that's important is because it's looking at this exchange between carbon dioxide and oxygen and what's happening. And this is called our respiratory exchange ratio, or our RER. And that essentially is our volume of CO2 divided by our volume of O2 being produced. So it's this ratio between CO2 and O2, and it's good in breath by breath. This is measured breath by breath. And this is an estimate of what we call our respiratory quotient, which is our indicator for which fuel source is being used in metabolism. So here, let me walk you through an example that I think might be able to help you just a little bit. So when we have glucose being metabolized, so glucose, remember, is a carbohydrate, and our molecular formula for glucose is it has 6 carbon atoms, 12 hydrogen atoms, and 6 O2, or 6 oxygen molecules. So this is literally just the chemical structure of glucose itself. Well, in order to metabolize, this glucose will bind with another 6 oxygen molecules here, and it will convert and rearrange itself in order to ultimately produce our ATP, which is, remember, our energy, right? This is just a rounded up formula looking at the 38 ATP. And it produces water as a byproduct. That's happening within the electron transport chain that this is occurring. And also throughout the Krebs cycle, we were seeing 6 carbon dioxide molecules being produced. So now when we look at our respiratory exchange ratio, remember that is the volume of CO2 divided by the volume of O2. So here is our CO2 and here is our O2. So we have 6 carbon dioxide molecules divided by 6 O2 molecules, which gives us a respiratory exchange ratio of 1.0. If you need to listen to that again, feel free to rewind and listen to that example again. But essentially, whenever we are burning straight carbohydrates, we are looking at a respiratory exchange ratio of 1.0. When we are in fats give us a respiratory exchange ratio of about 0.7 or so. So here's actually an example of what we're looking at. So here at an RER of about 0.7 or a 0.71, we're looking at the percentage of our calories, kilocalories that are being burned from carbohydrates is 0. We are not using carbohydrates at this time period, but about 100% coming from our fats. Okay, as we move from 0.7 up to 1.0, we are now looking at 100% of our kilocalories are coming from carbohydrates and none are coming from fats. So this is letting us know where exactly on our spectrum we are of burning fats versus carbohydrates. Now, when we're resting usually somewhere between like a 0.75 to 0.85. This is just during our measurement of resting, right? We're slightly more fats than we're higher percentage of fats than we are carbohydrates. So we are at rest burning more fat than we are carbohydrates. As we kick up into our exercise, moderate intensity exercise or lower to moderate intensity will actually drop us a little bit lower on this RER scale, and we'll be burning more fats, right, at our low to moderate intensity exercise. As we increase in our intensity, we will start to move to an RER of 1.0, and when we are actually like in glycolysis, because we've gone past what our oxidative system can handle, we are now moving into our 100% carbohydrates. So when we're looking at like intense exercise that we're doing that we can't maintain for long periods of time, we are looking at entirely carbohydrates are being utilized as our fuel source. This is kind of a graph. You don't have to pay attention to like all the intricacies of it, but it's looking at the two lighter colors here are showing that our energy sources are coming from carbohydrates. That is a abbreviation for carbohydrates, CHO. And then the two darker ones are showing from fat sources. So we're looking from rest, moving up to exercise. Notice that we aren't really expending a whole lot of energy at rest. However, a lot of it does come from fat sources. Here is our percentage from here to here is about the amount coming from fats, and here is from carbohydrates. So we start off and we're maybe 50-50, right? If I look at from here to here versus from here to here, it's about the same amount. So most of it's coming from an even split between carbohydrates and fat sources. As we maintain the same workload, but just increase in time, what ends up happening is we will actually start using higher percentages of fat sources compared to carbohydrates. So when we're maintaining at moderate intensity levels of exercise, we're going to be seeing higher percentages coming from our fat sources than we are from our carbohydrates. All right, so looking at it, and then actually we do have some recovery that needs to happen. This exhaustion is coming on because of steady state exercise that they ran out, not because of increasing in workload. So looking at the respiratory exchange ratio, we're looking at males and females, so it tends to be approximately similar. But here we are increasing in the workload, and as we increase in the workload, we'll start to see the RER increase over time. And remember, as we move from here up to here, increasing in our workload, we're going to see it move from fats, or here we were at moderate intensity, so we were somewhere a combination between the two, up to almost primarily carbohydrates. So it's showing an incremental exercise increasing your workload, that you move from mostly fats or a combination of fats and carbohydrates to mainly just carbohydrates.
And that finishes us out for the respiratory system. If you have any questions, let me know and I would love to be able to answer them.